Good morning to one and all. Myself, Dr. N. Muthukumaran, Assistant Professor, Department of Mechanical Engineering, Government College of Engineering, Dharmaburi. Yes. Today here I have shown a Unit 2 on power plant engineering. So in which we are going to discuss about the power cycles. There are many power cycles are there, like internal combustion power cycles or Otto cycles, spark ignition, DC cycle, compression ignition, and dual cycle, Brayton cycle, and combined cycles. These cycles are used in power plant engineering. Here, first, let's see what is the ideal cycle assumption. So before start these power cycles, let's see what is the assumption for the cycles. So here, first the air is the working fluid, right? It is circulated in a closed loop, is an ideal gas, isn't it? Exhaust and air intake are substituted with heat transfer from the system to the surroundings, right? Next, the combustion is replaced by heat transfer from an external source to the system. All processes are internally reversible and the gas specific heat is constant, right? The Cp and Cps. Next, the cycle does not involve any frictions and the pipes connecting components have no heat loss. Finally, neglecting the changes in the kinetic and the potential energies. These are all the assumptions which will be followed in the ideal gas cycles. Next, let's see what is the Otto cycle. Here, the Nicholas August is the inventor of Otto cycle for four-stroke engine. He was born on 14th June 1831 in Germany. In 1862, he began first experiment with four-stroke engines. The first four-stroke engine is shown. He died on 26th January 1891 in Cologne. So first thing, let's see what is the engine. So these are all the first here I have shown the engine, right? Here it is the engine in which we have the bottom dead center. Here it is a bottom dead center and here it is a top dead center. So there is a place which is called the clearance volume. What do you call it is? It is a clearance volume. The pistons moves from here to here. I mean the top dead center to bottom dead center. So here the combustion will be takes place. That is called the clearance volume, right? So here I am mentioning that what is the compression ratio, what is the displacement volume. This is the piston, right? Here that is a piston ring, this is a connecting rod, it is a smaller end, this is a bigger end, this is a crankcase. Here it is a spark plug, it is attached in the top of the bore. Here it is an inlet valve and this is an exhaust valve. These are all the engine components. Let's see what is the process in the Otto cycle. First one, process 1 to 2, isentropic compression process, and 2 to 3, here 2 to 3, constant volume heat added, I mean heat addition, and 3 to 4, isentropic expansion. What do you call it is? Isentropic expansion. And finally the 4 to 1, here it is, this is a constant volume heat rejection. This is the main process of Otto cycles. Let's see what is the four-stroke compression ignition engine. What do you call? Four-stroke compression ignition engine. Here you can see the engine components. Earlier slides itself we have seen what is the components. Let's see, this is a schematic view of four strokes: suction, compression, power and exhaust. Let's see what is the suction stroke. Here it is a top dead center. This is the bottom dead center. This is the cylinder bore. Inside the cylinder line will be there. This is the engine manifold. There is a intake valve. There is a exhaust valve. Right. This is a spark plug which will be attached in the cylinder bore. And this is the piston. The piston will be moves upward and downward motion. And this is the connecting rod. It's a crankcase, isn't it? Right. So let's see what is the suction stroke. Here, the fresh air fuel mixture will be drawn into the combustion chamber during suction stroke. The air and fuel will be drawn into the combustion chamber. Right. During the time, the pistons move from top dead center to bottom dead center. The inlet valve will be open, but the exhaust valve remains closed. Right. This is called the suction stroke. The next one, the compression stroke. Right. The compression stroke. During the stroke, the pistons moves from bottom dead center to top dead center. During this time, the inlet valve and the exhaust valve remains closed, isn't it? Both valve will be closed. So there is the fresh air mixture will be compressed, right? At the end of the compression here, the spark will be ignited. The spark will be ignited, right? This is called the power stroke. During this stroke, the pistons moves from top dead center to bottom dead center. During this time, the inlet valve and the exhaust valve remains closed, right? At the end of the compression here, I mean, what happened? The fuel is, burned. The fuel will be burned. Okay, so that enormous amount of heat energy will be liberated inside the cylinder. So what happened? That energy will be pulled down the piston to the bottom. From TDC to BDC. This is called power stroke. What do you call it is power stroke. And next, last one, the exhaust stroke. During the stroke, the inlet valve will be, the pistons moves from top dead center to bottom dead center. During this time, the inlet valve will be closed because the fresh air fuel mixture is ready for next suction stroke. So what happened? Here it is closed, but the exhaust valve will be open. So what happened? The pistons moves from bottom to top dead center. The burned gases will be released to the exhaust port. This is called exhaust. This is called the exhaust stroke. These are all the simple working function of compression ignition engine. Next, what is that diesel cycle? Rudolf Diesel in he was born in 1858 at Paris. After graduation, he was employed as a refrigerator engineer. However, his true love was in engine design. In 1893, he published a papers describing an engine with the combustion with a cylinder. The internal combustion engine in 1984, he filed for a patent. He filled a patent for his new invention, the diesel engine. He operated his first successful engine in 1897. This is you can see the schematic view of spark compression ignition engine. Here you can see the gasoline engine. Here you can see the diesel engine. In spark, in which it is working under the Otto cycle. Here the air fuel mixture compressed at constant volume. The heat is added. Here it is a heat added. Here the air fuel mixture ready for combustion. Right. Right. Here it is the compression. In this diesel engine, the compression means diesel. Air is compressed first and then the fuel is added into the cylinder at constant pressure, heat addition. At constant pressure, heat addition. Next. So this is the PV diagram, TS diagram for diesel cycles, in which process 1 to 2 adiabatic, isentropic adiabatic compression. Process 1 to 2, it is the isentropic compression, and the 2 to 3, here it is addition of heat at constant pressure. Addition of heat at constant pressure. P2 equal to P3. Here in process 3 to 4, isentropic, adiabatic expansion. Adiabatic expansion. And finally the 4 to 1, here it is rejection of heat at constant volume. Rejection of heat at constant volume. These are the cycles which will be applied in the diesel cycles. Next, we'll see what is the Brayton cycle. It is called Joule cycle. Another name is called Joule cycles. Here it is the simple schematic view here I have shown, in which we have compressor, turbine, and the combustion chamber. Right here, fresh air is drawn into the compressor. It is compressed. And after that, the fuel will be coming to the combustion chamber. The compressed air will be sent to the combustion chamber. What happens? Air will burn with the fuels. The fuel will be burned with the air. What happens? The gas will be formed at the higher pressure and higher temperature. And here in turbine, it is expanded. So work will be output. After expanding the work, the gases will be released to the atmosphere. This is a simple working function of Brayton cycle. So here I have shown the PV diagram and TS diagram for Brayton cycles.